Hello, everybody. We're going to go ahead and cover atmosphere right now. So you want to go ahead and put that in table of contents in your notebook. Start on the next page of notes. Put in the top center of the page, box it in, put today's date next to it. If you don't have your notebook, once again, you can just put on a piece of paper, and then later, when we return to school, go ahead and insert the notes into your notebook. Okay, here we go. Earth's atmosphere is a mixture of gases, obviously. 78% nitrogen, 21% oxygen, other gases sustain life, protects us from solar radiation. It says a thin sheet, which is kind of funny. That thin sheet is actually 60 miles thick from the Earth's surface to the upper limits of the atmosphere. A relative comparison, if you had a basketball wrapped tight with plastic wrap, or like you think of saran wrap, that would be the same ratio, basically, the same comparison. There's different layers and levels of the atmosphere. So the layers, you have troposphere, then you have the stratosphere, mesosphere, and thermosphere. As you can see in the diagram over here, those on the right side. And the levels, you have the tropopause on the left side, stratopause, and then the mesopause on the left side, layers on the right side. Air above exerts pressure below. That's where we get air pressure from. So on a typical day at sea level, typical pressure is 14.7 psi, or pound per square inch. And that's basically because you have 60 miles of a column of air, so 60-mile column tall, on top of every square inch of your body, and that's what creates that pressure. Comparison, that would be 101.3 kilopascals. Like I said, that's a column 60 miles tall, sitting on 2 thumbnails, would be 1 square inch roughly. Density and pressure higher, closer to ground. Obviously, you go to higher altitudes, then the density and the pressure decrease, but that's a typical day at sea level, 14.7 psi. So atmospheric conditions, aerospace engineers use a standard to compare measurements such as speed. So we use these numbers here, 15 degrees Celsius and 101.3 kilopascals, or 59 degrees Fahrenheit and 14.7 psi. What this chart here is showing is that as you increase altitude, so here if you're at sea level, increase altitude, so it's 2 degrees Celsius per 1,000 feet. So you have plus 11 degrees, plus 7 degrees, plus 3, minus 1, negative 5 degrees at 10,000 feet, and that's in Celsius. And the same aspect here, you have a pressure at sea level, and this is inches of mercury. You have 29.92, and then it's 1 inch of mercury per 1,000 feet. So you have increase in altitude, but a decrease in pressure. By the time you get to here, we have 19.92. That'd be about 10,000 feet. 19.92 would be your pressure, inches of mercury. The lapse rate in troposphere, 11 kilometers. So you need to go ahead and write these two equations down. These are equations that we'll use to find the absolute temperature and absolute pressure. The top one being temperature, so 15.04 degrees Celsius, minus 0.00649 degrees Celsius per meter times H, and H would be your height in meters. So you'd enter that number into the equation, H, and then multiply it times 0.00649, and subtract that from 15.04 degrees Celsius. For the pressure, you would take the temperature you found in the above equation, add 273.1 degrees Celsius. That's Kelvin per degree Celsius. That's just a conversion factor. But you add that to 273.1, divide it by 288.08, and then take that number within the brackets and then put it to the power of 5.256, and then multiply that times 101.29, and that'll give you that pressure right there. And that pressure is going to be in kilopascals. Once again, height in meters, and our temperatures are in degrees Celsius because we're in the metric system here. Air density changes based on pressure and temperature. So generally, air density lowers as it climbs to higher altitudes. So this time we're looking at rho. Right here is this symbol, the Greek letter rho. So rho is going to be our air density, and that's going to be our pressure that we would have found just a second ago. The temperature we would have found before that, let me find my cursor, before that, add 203.1 degrees, times it by 0.2869, divided by the pressure, and that'll give you your density, and that density is going to be in units of kilogram per meters cubed. So I'd go ahead and write this equation down for rho, and then also get your variables with units too. But those are important to remember. Mount Everest is 8,848 meters, or to us 29,029 feet tall. Similar altitude of jet aircraft. Climbers acclimatize over a long period of time or breathe supplemental oxygen. So a lot of time when they climb Mount Everest, they actually will carry kind of oxygen with them. It's just easier than trying to acclimate themselves to the that altitude. It takes a long time to do that. But still looking at flying an aircraft about that same altitude. Pilots must react quickly to receive supplemental oxygen if cabin loses pressure. So that's true for all aircraft. They do have pressurized cabins, but then if there's a pressure loss, then they have oxygen masks to help them get oxygen until they get to a lower altitude, where hopefully oxygen will be more available. And causes of a pressure loss: fuselage integrity failure, so there's a leak somewhere, hole, fracture, something happened, and then window failure, which could happen. That's why you never see square windows on any commercial airliners. They're always round or oval shaped, because these squares with the corners create weakness points. Here we see a plane breaking the sound barrier. When you break the sound barrier, the plane actually creates a cone. Now this is a 2D picture, but if you look at a 3D view, it'd actually be a cone, the tail end of that aircraft. That's because what it's doing is going so fast, it's compressing the air, and the moisture can't get out of the way fast enough. So when it's moving, it actually makes the moisture condense around the aircraft, and that's the cone we're seeing right there. Aircraft speed: air molecules must move as the aircraft passes through atmosphere. Air compressed at speeds beyond 400 kilometers per hour or 250 miles per hour. Air resistance is significant when close to speed of sound. So transition to beyond speed of sound creates shock waves and sonic booms. And of course, if you ever seen the movie The Right Stuff, when Chuck Yeager breaks the sound barrier, that boom they hear for the first time, they thought he blew up or exploded or crumbled, but that was not it. He actually broke the sound barrier. That's kind of sometimes if you watch YouTube videos, the Navy, when they're out on the sea and they get bored, they'll have a plane fly over the flight deck and crack the barrier. Just so the crew can hear the boom and feel the shock wave when it passes them. Mach speeds, so M, decimal number representing the true airspeed relationship to the local speed of sound, 1,225 kilometers or 761 miles per hour at sea level and standard conditions. I wrote this last part down, the kilometers and miles per hour at sea level standard conditions, because as you change altitude, the Mach speed also changes. That's important to note. So subsonic speeds, when I write this down, is less than Mach 1, which obviously is commercial personal aircraft. Supersonic, Mach 1 and Mach 5. And then you have hypersonic between Mach 5 and Mach 10. You have high hypersonic, which is between Mach 10 and 25. And then, of course, the speed of sound changes with temperature, which then also is pressure and altitude, all those things. So it does change. Higher altitudes are cooler, so Mach threshold is lower. So you actually can break the speed of sound at a higher altitude because it lowers the threshold. And that is it. It's a really quick, short PowerPoint. I wish we could be there in person to discuss it, but obviously we cannot since they just canceled school again tomorrow. So if you can look at 124 on PowerSchool Learning, open it up for you right now. If you can print it, great. Go ahead and print it. If not, you can try to answer it in your notebook or anywhere, and then transpose those answers and your work to the paper when we get back to school, hopefully Friday at this point. And I already have copies made, ready to go out to you. I just didn't pass them out, so I didn't think we would miss 3 days in a row again. So here's the activity 124. There's 2 math problems. They want you to use Excel. If you don't have Excel at home, remember you always have a free online copy. If you go through the Linmar main page, there's a free copy of Office. You can do it online, or you can download it and install it free. I think they give you up to 5 free copies too of Microsoft Office. So anyways, number 3 is an Excel problem, and then you have 2 conclusion questions. On PowerSchool Learning, I actually have an example to show you how your spreadsheet could look after you're done with it. Okay, but here's a PowerPoint. There's my example for the spreadsheet, and here's the actual activity itself. So if you have any questions, email me or send me a text to remind. See you guys, and hopefully we'll see you soon.